Welcome. Let me say more about curvatures which live on higher dimensional parts of space. So Euler characteristic is the total energy of space. So that works in a simplicial complex, for example, in a delta set, or in a graph framework where the k-dimensional simplices are given by the complete subgraphs. And we have a Dirac matrix, which is given by the exterior derivative. And so we have differential forms are just functions on these k-dimensional parts of space. So it's a finite dimensional vector space, and these curvatures are k-forms. So the k-curvature will be a k-form. I don't know of anything which exists like this in the continuum. There's the Ehresmann curvature, but has nothing to do with that. But we have here a generalization of the curvatures which live on vertices, which is k0. And here is the general definition. So the curvature has a contribution from the inside of the simplex. That's kind of something which doesn't exist in the zero-dimensional case. And then the part which is outside. There are two extreme cases. One extreme case is if you have k equal to 0 and curvature lives on the vertices. That's what we usually consider to be curvature, where we get the Gauss-Bonnet-Chern, for example, for even dimensional manifolds in the continuum. And then we have also an extreme case where the curvature is a form, a D form. And so I call this facet curvature. It lives on the highest dimensional parts of space. Now, in order that that works, we need the k-dimensional parts of space to generate the whole space. So this is an example. The frog graph is a graph which is two-dimensional, right? Because there are two triangles, but the two triangles don't generate the whole frog, right? There are parts which are one-dimensional. So the curvature, so the face curvature, which is here, actually one, would not generate the, would not add up to the total Euler characteristic, which is 1 here for the whole frog. So the proof of Gauss-Bonnet is almost tautological. We just take this omega x and we shove it to the k-dimensional part. We don't shove it to the zero-dimensional part like for the usual curvature, but we shove it to the k-dimensional part. And so that's the proof. And it's quite amazing that in the discrete everything is so simple when you compare with the continuum. Now, in order to see that the continuum is really kind of corresponds to this, one has to look at curvature a little bit more generally. One can define, first of all, Poincare-Hopf indices, which are integers, which are divisors, and this generalizes also here. We just don't shove everything from a simplex equally to the lower dimensional parts or higher dimensional parts. What we do is we just attach it to one part only. So that's kind of, that doesn't split things up. So that's why it's an integer. It's kind of like a deterministic way how the energy of a simplex y is going to a k-dimensional simplex x. So we add them all up, these energies, and that can be expressed using Euler characteristics. So it's the Poincare-Hopf theorem. And then what we can do is we can just look at expectations of such indices. I like the framework where, you know, we have just the functions of the function, I mean, these special k-forms which are, so locally injective means that the adjacent parts have different values. So that's for in a probabilistic setup. For example, if you take a product space, that's the case for almost all. So if you take the expectation here with a, you know, very symmetric measure, what you get is the usual curvature, where everything is kind of distributed equally to the different parts of space. But so this index expectation is something which happens in the continuum. We take the continuum, we take a manifold in space, and what you can do is you can embed it in a Euclidean space. That's by by the Nash embedding theorem. You can do that isometrically, and then you can look at Morse functions given by linear functions. Almost all of them are Morse functions, and you look at the indices in each and you average them over all possible functions, and what you get is the usual curvature. So that's why this curvature here corresponds to the, you know, well-known curvature in the continuum. It's the same thing, but it's much easier because we can access the k-dimensional parts of space, and so we can also throw the curvature to the k-dimensional parts of space. So it's something which you can now also animate. And I promised that last time to show. So what we can do is we can look at the wave equation. So with a d, it's very easy to solve this wave equation. Like cosine dt solves the wave equation, because if you take twice the derivative with respect to t, you get minus d squared. So it's the wave equation. The Dirac operator is the square root of the Laplace theorem. We don't have to work here in the discrete. We don't have to build Clifford algebra. It's already built in, this Clifford algebra. So we don't have to build Dirac matrices and all these things, gymnastics which we need in the continuum. This already is just built in. And if we define a delta set like that, it's actually given to you already. So that satisfies the wave equation. And then there is the McKean-Singer symmetry, which I consider absolutely central to the whole story, because it is essentially the elliptic regularity replacement, what you have in the continuum. It really you know, gives you all the proofs. First of all, it gives you also here that the supertrace of the cosine dt is just the Euler characteristic, because you just make a Taylor expansion and you have one. Supertrace of one is by definition the Euler characteristic. And then you have the supertrace of d square, which is supertrace of L, which is 0. All the supertraces of Lk are 0. That's McKean-Singer. And so that doesn't change. You can take that e to the zt of any complex z. So heat equation, wave equation. And then we can now take these fundamental energies omega x, we can now just animate, right? We can just take cosine dt xx. And then when we take the supertrace of that, we get also the Euler characteristic. But now we can take these energies and shove it to the k-dimensional part. And so what we get is the animation of the k curvatures. And I did that kind of just for illustration. Maybe I show here the animation. I did that just in a case of a two manifold. I took a two-dimensional, you know, a two-dimensional surface. Actually, I just took a sphere, kind of a random sphere, and I was then computing these curvatures. So the zero-dimensional curvature, which lives on the vertices, the one-dimensional curvature, which lives on the edges, and the two-dimensional curvature, which lives on the faces of the polyhedron. And then one can look what happens when you animate them. So each of them satisfies Gauss-Bonnet, and you can just now see the wave a little bit, you know, in a different way. I also here kind of computed quickly the curvatures, so in the special case of a three-dimensional manifold. Manifolds are special in that the unit spheres are spheres, and that's very special. That, for example, means the spheres are in Somerville, so they are symmetries. And the whole thing for me, the research on these things started with this curvature and also then the observation that for manifolds, for odd-dimensional manifolds, I saw that the curvature was always zero. I could not prove that first, and then I developed this index expectation just to prove this. So later I saw this as a Dehn-Sommerville relation. Now, in the case of facet curvatures, higher dimensional curvatures, I also saw experimentally first that the curvature is always zero. Also, if you animate it, it always remains zero. There's no motion there for odd-dimensional manifolds. For even-dimensional manifolds, that's not true, or in general it's not true, but for odd-dimensional manifolds it's true. And one can see this also not yet Dehn-Sommerville. I call it Dehn-Sommerville, but I don't yet see the Dehn-Sommerville relation, but I see it just using this index expectation, this symmetry. If you take a Morse function and you take the negative Morse function, and it is zero, so the index is antisymmetric. When you take minus g, you get the minus index. For odd-dimensional manifolds only, not for even-dimensional. For odd-dimensional, that's also classically true, by the way. And so this is kind of one of the easiest way to see that an odd-dimensional manifold has zero Euler characteristic. So that's what I wanted to say today. Thank you.